The first lesson in the reactions and stoichiometry unit is on chemical reactions and equations. Here are our learning targets for this lesson. You can see there are three here. The first, we want to be able to identify chemical reactions. So a chemical reaction, if you want a definition for it, it is a process where one or more substances will produce one or more new substances. And to help us understand this idea, here is a schematic of a chemical reaction ongoing. Notice the word reactants here on the left and the word products on the right. Here we're showing two different reactions. For the first one here, we have some compound made of A and B, and it is reacting with element C. And notice after the reaction occurs, we have an arrow here to show that we have at least one new substance produced. We have now element A, and then we have compound BC. So we get new substances there. And then in the second reaction here, we have two compounds, compound AB reacting with compound CD, and we get AC and BD. Again, notice we get at least one new substance produced, so thus a chemical reaction has occurred. What we want to be able to do is identify using observation when a chemical reaction has occurred. And there are a few common pieces of evidence that we can use to help us identify when this in fact has happened. The first would be a color change. If you have a substance or substances and you mix them together, or you don't really have to mix anything, but if you notice a substance seems to be changing color, what that's telling you is a new substance is being produced. That color change is actually not the original substance. You're seeing something different there. So here's a picture of what that might look like. Notice here we have some sort of clear solution, and then we can see the end of a pipette here. Some solutions being dropped into this flask here, and then when these two mix, we get some sort of yellow substance here. So we get a color change. That yellow substance is obviously something new, because substances don't just randomly change color. Another would be an odor change. This we are very familiar with. Here's a picture of some spoiled milk. Now, obviously, you can just look at that picture and tell that you would not want to drink that. That would not taste very good. But the reason why an odor change can be a good piece of evidence for us, let's say you had a carton of milk and it was just past the expiration date, maybe 1 day past it. You could probably go ahead and take a whiff of that and see how it smells. And most of us, if it smells fine, you're going to go ahead and drink it, because obviously that chemical change hasn't undergone yet. But if you smell it and it obviously does not smell like milk, that tells you a chemical change has occurred, and you're not going to drink whatever's in the carton at that point. Another one that we really would not use too much in the chemistry lab, simply because could be very dangerous, would be a taste change. However, this is certainly something that you might do at home, or you were certainly experienced with. Here's a good example. Here we have a banana that is quite ripe. Obviously, a banana that has had several days to ripen tastes very different than a banana that you might purchase when it's all yellow, or maybe even a little hint of green on the outside there. Now, obviously, this is another example as well of a color change. Another very common piece of evidence that can tell us a chemical reaction has occurred is a release of energy. Here we have a picture of something burning. We're giving off heat, light. There's probably some sound as well. All these things are different forms of energy that are being released as the reaction occurs. That is a very good piece of evidence of a chemical reaction occurring. And then one more that is very common is the production of a new state. So here we have an example where obviously there's some sort of gas being formed here in this reaction. Now, one piece of confusing evidence that can come up would be phase changes. Oftentimes students will see this point here, production of a new state, and think, okay, well, if I put water in the freezer and wait a few hours, it'll now be solid. It will obviously turn to ice. So that's a chemical change. Well, no, that's not. That is simply a phase change. That's still water there. So that would not be an example of a chemical reaction. But if we mix two substances, or three, it wouldn't have to just be two, and then just simply that mixing causes a new state to be formed, a gas forming from a couple of solutions, as we see in this example. Maybe we mix two solutions and we have a solid formed. Actually, that's what's going on here in this picture with the yellow substance being formed. That's actually a solid that's being formed there. That would be an example of a chemical reaction that we can see from the production of a new state. All right, so we should be able to identify chemical reactions based on that evidence. Next thing we want to be able to do is to describe the general format of chemical equations. So the general format of any chemical equation, or what a chemical equation is, it simply uses symbols and formulas to represent the substances involved in a reaction. If you ever see this notation here, rxn, that is very common shorthand in chemistry for the word reaction. So really, what we're saying here is we're just writing an equation just like you would in math. If you want to write 7 plus 4 equals 11, in math, you don't actually write out the words 7 plus 4 equals 11. You use symbols for those. We have a symbol for the number 7. We have a symbol for the plus sign. Likewise, a symbol for 4 and equals and the number 11. And we use those to write our equation. Same thing in chemistry. We don't actually have to write out the words that make up the substances. We can use their symbols and formulas. An equation always has the reactants on the left side of the equation. It could be a single reactant or multiple reactants. Thus, you see there the S in parentheses. And then we separate the reactants from the product or products, not with an equal sign, but with an arrow. The arrow always points from reactants to the products. And again, notice we could have a single product or we could have multiple products. Here are some examples of some equations. So here we have an equation. If we look at the symbols here, some things should look very familiar to us. We have H2O, we're familiar with that being water. We have H2, that would be hydrogen. We have O2, that would be oxygen. Now there's some other things here that you might not be so familiar with. Notice in front of a couple of these, the water, the formula for water and the symbol for the hydrogen, we have the number 2. And then we have an arrow here, we have a plus sign, and then next to each of these we have a letter that's in parentheses, the G next to the two elements here, hydrogen and oxygen, and an L. I know that might kind of look like the number 1. It's actually the lowercase little letter L there in parentheses next to the formula for water. Well, we could write this exact same equation using a sentence, and here's how that sentence might read, and this will help us understand some of these symbols we might not be familiar with. The sentence might read something like this: 2 molecules of liquid water produce 2 molecules of hydrogen gas and 1 molecule of oxygen gas. So from this sentence, you could probably see here that the 2's out front of the water and the hydrogen here are telling us how many molecules are involved. And the fact that there's not a number there in front of the oxygen tells us there's 1. We call these numbers out front of the symbols and formulas coefficients, which you are very familiar with from math. And as same thing in math, if there's not a coefficient in front of a symbol, it is understood to be 1. So notice there is no coefficient out here in front of the O2, so that is understood to be 1 molecule, in this case, of oxygen gas. Notice that the letters that are in the parentheses correspond to the physical states. We're told we have 2 molecules of liquid water, the L standing for the liquid, and then we get hydrogen gas and oxygen gas. That's why we have the G's here in parentheses to show those are both in the gas state. Notice the arrow here is corresponding to the word produce in the sentence here. 2 molecules of liquid water produce 2 molecules of hydrogen gas. So anytime we see this arrow, that tells us we have a chemical reaction going on. We're going to get at least 1 new substance. There is more than 1 word that we could write for that. It would not have to say produce. It could say it forms 2 molecules of hydrogen gas. It yields 2 molecules of hydrogen gas. Several different things we could say there. And then notice the plus sign is substituted for the word and. Now, that would not always have to be the case. That is often the case. Anytime we have multiple substances on one side of the equation, notice here we have two different products, both hydrogen and oxygen are formed. The symbols and the formulas are always separated by a plus sign. Here's another example. Now notice we again have symbols and formulas just like we had in the last equation. Notice this time though there are two different substances on the left side, meaning we have two reactants. In this case we have silver nitrate and we also have sodium chloride. And also notice we have a new symbol here in parentheses, the symbol AQ. AQ. Now here is a sentence for this reaction that would correspond to this equation. The sentence might read, solutions of silver nitrate and sodium chloride produce solid silver chloride and aqueous sodium nitrate. Now, the only real new thing we have in this equation compared to the last one is this symbol AQ. And notice in the sentence here, we're told that these two reactants are solutions of silver nitrate and sodium chloride. Well, the reason we put the symbol AQ there is it stands for the word aqueous, and actually that word is used later on in the sentence. We can see here aqueous sodium nitrate. When something is aqueous, that simply means it's dissolved in water. So we have a solution of silver nitrate, we have a solution of sodium chloride, and unless we are given information otherwise, that tells us it is dissolved in water. So aqueous means dissolved in water. And you might be able to figure that out anyway because notice the root word there is aqua, referring to water. All right, so we've seen some examples of chemical equations. What we should be able to do now is look at some symbols in these equations and know exactly what it is that they mean. Some common symbols, many which we've already seen here. If we have an arrow, that separates our reactants and products. It might be read as yields, produces, forms. You could probably look up this in a thesaurus and find all sorts of other words that you could use for it. Physical states are indicated in parentheses. We saw each of these in those examples. Solid being an S, liquid L, gas is a G, and then aqueous being dissolved in water, that would be AQ. Another common symbol that we did not see in either of those examples, if you see a triangle, often it would be written above the arrow. That means you're heating the reaction, or you're heating the reactants in order to get them to undergo the reaction. So we've looked at some basic chemical equations, seen the general format. What we should be able to do now is simply write equations given a sentence that describes them. So here's an example. We're told solid copper reacts with a solution of silver nitrate to form solid silver and a solution of copper 2 nitrate. We want to be able to write the chemical equation for this reaction. So just reading the sentence here, solid copper reacts with a solution of silver nitrate. Those are my two reactants, copper and silver nitrate. So those will go on the left side of the equation. The symbol for copper, we can look that up on the periodic table, that is Cu. We're told it's a solid, so I'll put S in parentheses there. To show that it's reacting with silver nitrate, I will separate the symbol for copper and the formula for silver nitrate with a plus sign, so I'll put a plus sign next. Now I need to write the formula for silver nitrate. That would be AgNO3. Here's where your nomenclature becomes very important. We need to be able to write these formulas correctly. So the charge on a silver ion is 1 plus, the nitrate's 1 minus, so AgNO3. And notice we're told it's a solution. So again, we just mentioned this. If it's a solution, that tells us it's dissolved in water, unless we're told specifically it's dissolved in something else. So AQ or aqueous would be the physical state. Now these two substances are going to react to form some new substances. So we will show that by writing an arrow, again pointed to the right. And then we're told that we form solid silver, so that would be Ag, and then S would be in parentheses to show it's a solid, and a solution of copper 2 nitrate. Notice we separate the symbols for the two substances using a plus sign. The formula for copper 2 nitrate, CuNO32, We're told it's a solution, so AQ in parentheses. Another example. We're told a molecule of liquid propane, and notice here you're given the formula, because at this point we probably haven't learned the nomenclature for this is actually an organic compound. So I'm just telling you here it's C3H8. It burns in 5 molecules of oxygen gas to form 3 molecules of gaseous carbon dioxide and 4 molecules of water vapor. So here we have 2 reactants like we did before. One of them would be liquid propane, the C3H8. Notice we're told it's a liquid propane, so thus the lowercase letter L here in parentheses. And then it's reacting with 5 molecules of oxygen gas. So plus, to show we have a different substance. And then my symbol for oxygen gas is O2. Remember, oxygen is one of these 7 diatomic elements, so thus O2, it's a gas, so G in parentheses. And then we're showing there are 5 molecules there by putting the coefficient 5 out front. Now these two are going to react to form something different, so here's where we use the arrow. And then we're told that we get 3 molecules of gaseous carbon dioxide. Formula for carbon dioxide is CO2, so 3 CO2 gas plus 4 molecules of water vapor. So plus 4 H2O, and then we're told it's water vapor, meaning it's in the gas state, so a G there to indicate that. All right, here are a couple of practice problems. I'm just going to ask you to do what you just saw in the examples there. Write the chemical equation for each. I would pause the video, try it yourself, and then see if you did it correctly. All right, I suppose you've had a go at this already. When potassium metal is placed in water, hydrogen gas and aqueous potassium hydroxide are formed. So here we just have one reactant. Not one reactant. We have 2 reactants when potassium metal is placed in water. So potassium metal and water would both be our reactants. So potassium, that's K. Now we're told it's a metal, so ask yourself what physical state is that? That would be a solid. Sometimes you just have to use some intuition and some common sense in order to write these correctly here. So if it's a metal, probably going to be a solid, so thus C in parentheses. And then if we place it in water, so plus the formula for water is H2O. Pretty good chance it's liquid water unless we're told something different. So I'm going to use the lowercase l there in parentheses. And then we're told hydrogen gas and aqueous potassium hydroxide are formed. So those are the products. So I need my arrow next. Hydrogen gas, just like oxygen, is one of the diatomic elements, so H2 gas. And then the formula for potassium hydroxide would be KOH. Potassium is 1 plus, hydroxide is 1 minus, so there's a formula there, and then the AQ to show it's a solution. All right, last practice here. Again, go and try this on your own. We have solid iron 3 oxide is produced when iron metal reacts with oxygen. Notice on this one, the first substance in the sentence is actually a product. We're told that solid iron 3 oxide is produced. Oftentimes, students will look at this, they'll see the iron 3 oxide come first in the sentence, and they'll automatically put it on the left side of the equation. Notice how the sentence is written here. We're told that that substance is produced when something else occurs. So this is the product. Our reactants here are iron metal and oxygen. So iron metal, again, that would be a solid. We just talked about that in the last example there. And it's reacting with oxygen, so plus O2 gas. Again, we're not told it's a gas, but if we just think about what oxygen is, pretty good idea that it would be a gas, unless we're told differently. And then those two will react to form the iron 3 oxide, which has the formula Fe2O3. We're told it's a solid, so S in parentheses there, and there is our equation. All right, this completes the first lesson here on our reactions and stoichiometry unit. In this video, we were able to identify chemical reactions. We looked at different pieces of evidence to know they had occurred. We looked at the general format of chemical equations and how we go about writing those, and we got some practice on writing chemical equations.